Hello and welcome to section 3.9 differentials. And so remember, if you have any questions, please ask in class. Look for these out online. So what we're going to do is we're going to talk about a different form, and we're also going to talk about this example right here. I've seen this example done many times on the AP test, where they give you a function and they ask you to use the tangent line approximation to find out what's happening at near a point. So they'd say like something like what's happening at if they wanted at the point, say 1, they would say at like 1.2, and then you'd use this tangent line approximation to do that. And so basically what we're going to do is we're going to find the tangent line to this function, and then once we find that, we'll put it here, and then we'll use these. What I've done is I've already plugged in these values as we approach 0, and to see what's happening for my original function, and we'll see how the tangent line approximation is close to that. And so basically, if I go ahead, so I got to differentiate this function, which gives me, I believe, cosine of x, and if I put in 0 in my derivative for cosine of 0, I believe I get 1. So that means that my slope is 1, and so at my point at y minus 1 equals 1 times x minus 0, which basically means my function is x plus 1. And so that's my tangent line equation, y equals x plus 1. If I put in negative 0.5, I get 0.5. If I put in negative 0.1, I get 0.9. If I put in 0.01, I get 0.99. If I put in 0, I get 1. If I put in 0.01, I get 1.09. If I put in 1, I'm subtracting there, 0.1. If I put in 0.01, I get 1.1, and if I put in 5, I get 1.5. Alright, so that's basically saying that my tangent line approximation is close enough. And that's what differentials are all about. We're going to use a tangent line approximation instead of the actual delta x that we have been dealing with. And so that leads us into our second example when we're comparing our delta x to our dx or dy dx. And so they have to tell us that how accurate they want our dx to be, and that would be 0.01, which would be the same as our delta x. And so we need to know that we're going to say that delta y is going to be approximately dy, which means that delta y is approximately f prime of x times delta x. And so we need to kind of remember these when we're dealing with this. And so as we go through this, since y is x squared, then we know that f prime of x is really 2x. And so if we know all of this, we can go ahead and say we can approximate our dy by saying that we know that that is going to be 2x, and we know that when we plug in, so we're going to say f prime of x, our dy is f prime of x dx, and so that would be f prime of 1 dx, which basically means that f prime of 1 is plugging in 1 into 2x, which would just be 2, and then we multiply it by our dx, which is 0.01, which will give me basically a value of 0.02. So that is our approximation for our delta y. And so then if we wanted to use the actual delta y that we know and love from way back at the beginning, we'd say f of x plus delta x minus f of x. And so that's what we learned way back in the beginning when we were doing the limit process. And so we would go ahead and plug in what we know, and x plus delta x is 1 plus 0.01, so it would be f of 1.01 minus f of 1. And so we're just plugging in our values just like we normally would, and when we put in 0.01 into f of x, we get 1.01 squared minus 1 squared, and then this will end up being, when all multiplied out, will give me a value of 0.0201. So this little extra stuff down here isn't really causing any problems, and so we could have used a tangent line approximation to also do this, and it would give us basically the same value. And like I said, the tangent line approximation is is what we're going to use on the AP test. And the tangent, to find our tangent line, we would have said something like, well, f of x is our x squared at x equals 1. We want to find out what's happening at 1.01. That's really what we're trying to find out. And so we would go ahead and say, oh, well, we could say if we took the derivative of this, f prime of x would be 2x, which means my slope is 2. So we'd say y minus, and then we'd plug in our 1. We'd say y minus 1 equals 2 times x minus 1, which gives me an equation of 2x when it's all simplified out, 2x minus 1. And then by plugging in our 0.01 in for x, you could see that we would get our value that we are looking for would be something like 1.02, and that would be the approximate to our other value when we would have our, if we just did f of 1.01. And that would be pretty darn close to the same as this guy right here, which is just plugging in 1.01 into the function. So we're just basically using a tangent line to approximate what's really happening. And so that's kind of the whole idea of this. And so now we're going to talk about differential notation versus standard notation. And if we took the derivative of this, we would have gotten 2x. If we took the derivative of this, we would have gotten 2 cosine of x. If we take the derivative of this, we get negative x sine x plus cosine x, using our product rule. And then the last one, we would have gotten negative 1 over x squared. And so differential notation just said that if dy was basically the same as f prime of x times dx. That's differential notation. So we're getting rid of the dx, so this one as a differential would be 2x dx, the derivative times dx. This one would be 2 cosine x times dx. This one would be the whole thing, negative x sine x plus cosine x dx. And then finally this guy would have been, and it might have been written like this, dx over x squared. They like to put the dx on top when there's a 1 up there. And so this is just kind of chain rule notation, and this is just the notation that we're going to be using from here on out. So then finally we get to an example where it says find the differential dy of this. And so remember that these guys are approximations, so I'm going to go through and differentiate this. And so remember that dy approximation is f prime of x times dx. So when I differentiate that, I get dy will equal, and now I'm going to take a chain rule to do this. So differentiating the outside gives me cosine 3x, and then when I differentiate the 3x, it's just times 3, and then remember that I get a tag on my dx, so that is my final differential form. That's what I'm looking for. In my next example, same idea. They're asking me for differential form again, so I'm going to remember that dy is the same as f prime of x dx, and so then I'm going to go ahead and differentiate this, and so f of x, I'm going to write it as dy equals 1/2, and this is going to take a chain rule, x squared plus 1 to the negative 1/2 times 2x, and then I will add on my dx, and so then with a little simplification, my 2's cancel out. I'm left with x dx on top, all over the square root of x squared plus 1. And so that is my differential form. And so then finally, we can use our tangent line approximation to approximate what's happening at the square root of 16. And so we would just say, oh, well, I know that we're talking about f of x plus delta x in this case, which would be approximately the same as f of x plus f prime of x dx. And so in this case, if I know that my f of x is the square root of x, and this f prime of x turns into 1 over 2 square root of x dx, I can then go ahead and plug in what I know. And if I know that x is 16 and dx is 0.5, then I could say, oh, well, the square root of 16 plus 1 over 2 times the square root of 16 times 0.5 will get me my approximation, which basically comes out to be approximately 4.5 4.0625. And that would be the same as, but this is basically if we couldn't do it on a calculator, we couldn't come up, if we didn't have a calculator access to it. And if we went through and did f of 16.5 as my original thing, it would be just the square root of 16.5, which is approximately 4.0620. And we will talk more about this. This is kind of using our tangent line approximation. Remember, if you have any questions, please come to class prepared to ask them.